study and review of this material. 4 key points about this particular reaction. The first one is most important, is that bond breaking and bond formation. We're going to break a bond and make a bond. And this happens at same time. So both our new bond that's forming and the leaving group bond that's breaking, it all happens at once. This particular type of process where all these reactions happen at the same time is referred to as a concerted process. The alternative, where first a bond breaks and then a bond forms, is called a stepwise process. But when everything happens at once, it happens in concert, or it's a concerted process. When the nucleophile attacks the substrate, it does so via backside attack. Happens via backside attack. In essence, the nucleophile's lone pairs of electrons attack into the sigma star antibonding orbital of the substrate, basically the substrate X bond. Okay? So the way this works is you can go back and review, if you really want, sigma and sigma star. Studied them earlier with Dr. Marinas, I'm sure, and learned about them in general chemistry. But the electrons from this nucleophile go into the antibonding orbital of this particular substrate. The mode of attack and the location of that antibonding orbital is right here, our backside. And then this logically leads to the inversion of stereochemistry. If it only attacks from the back and hits this, the groups push that way as the leaving group leaves in the previous slides, the stereochemistry will invert. This was named after someone, sometimes you might hear it called a Walden inversion of stereochemistry. That's not so important for us, this name Walden. Key point is that the stereochemistry flips if there is a chiral center. If there's not a chiral center, then stereochemistry still flips, but we don't see it in the resulting product if 2 of the groups are identical, like hydrogens. And the 4th point, which is a minor point for us this semester, is that the rate of the reaction, speed at which it takes place, is a function of a rate constant k, small k, multiplied by the concentration of the substrate and the concentration of the nucleophile. This particular reaction is dependent, its speed is dependent on both the substrate and the nucleophile, and so the reaction is said to be second order or bimolecular, meaning it's dependent on 2 different molecules, and this is where the 2 comes from in SN2, that both the substrate and the nucleophile matter. I think we should actually say that here too. It's kind of a subtle point. I understand many of you might feel uncomfortable seeing this rate equation here. That's normal. It's okay. Well, substrate and nucleophile matter. What that means by matter, we're going to see shortly. And this was also going to serve as a point of contrast. Right? This is going to serve as a point of contrast when we learn about the SN1 reaction. The SN1 reaction has many differences than this. That's also very, very less important than SN2. So we're going to do the heavy lifting on the SN2 reaction, learn about all these different features, and then when we finally do spend time with the SN1, a complement to this reaction, the differences will be immediately obvious, and you'll be able to easily digest it. So this might seem like we're going quite slow right now, but there's a reason for that I want you to master some of these bigger concepts, so when we contrast them later to the SN1 reaction, there won't be any confusion, I'm sure. Again, the rate, don't worry about it. I won't ask you to do any rate calculations. Those days are over, at least for general chemistry and sophomore organic chemistry courses. Someone else might ask you rate equations later and rate calculations, but it's not going to be me. Key point, though, is both of these things have an effect on the rate. If we increase the concentration of this or this, the rate speeds up, and that's displayed or exhibited by so-called bimolecular reactions. We're going to go back to basics here. We're going to draw just a generic nucleophile. We'll put 2 electrons on it. Just put a negative charge. We're going to draw some sort of substrate. Substrates are any carbon-containing compound. Draw a little bit more exotic one right now. We'll draw a cis-di-substituted cyclohexane. We'll put an X group here. This is going to be identified as our leaving group. We're just going to put a methyl group here for fun. And this is called a nucleophile, something that loves nuclei. This is important. This species here is called our substrate. This is important. You're going to have to study and learn about this and this. Reactions are typically done in a solvent. We haven't talked about this too much, as I've said 3-4 times now, but the solvent matters in this reaction. We're ultimately going to make a product. Obviously, that's important. And in this particular case that I'm drawing here, as we draw the product, we should note that the nucleophile has inverted its stereochemistry versus the leaving group. If we were to actually attack a ring with a nucleophile, and you could do this with your model kits, you would actually see backside attack would result in this leaving group coming out the top, this hydrogen getting pushed forward, and the nucleophile would be in the bottom position now. So when you see this applied to rings, this is what it'll look like. So this will be our product. We'll be focused on making products, predicting products, and that sort of thing. And the final thing that we're going to look at is our leaving group. I'm going to put a star next to the leaving group. So there's 4 species that I put a star next to here. Our nucleophile, our substrate, our solvent, and our leaving group. We're going to discuss all the little details about these 4 entities, how they affect the formation of this particular product. So the reaction up until a few minutes ago seemed quite simple, but there's many, many facets of it that we're going to learn about. Some of them are very simple, you'll digest easily, which is good for all of us. Some of them are going to take a little bit more time for you to sit down, think about, and contemplate. First thing, though, you have to master the mechanism. Nucleophile attacks carbon, backside, this leaving group leaves, so it's a 2-arrow process, and then it has some stereochemical consequence. That's the easy part. Let's actually now start chugging away at these 4 things that we're going to consider. The most important consideration is going to be our first consideration. Most important thing we can study or learn about is the nature of the substrate. I'm going to call our first thing that we think about in SN2 reactions the nature of the substrate. So we're going to learn about its nature, what it's like, and how that affects reactivity. Our substrates are going to be typically categorized as tertiary, secondary, primary, or methyl. And their reactivity is that methyl is the most reactive. It's much more reactive than primary, which is much more reactive than secondary. And tertiary substrates are unreactive or cannot undergo SN2 reactions. So for this we can say no SN2 reactions for tertiary substrates. They simply will not react following the mechanism that we had drawn previously. So let's look at this just a little bit more detail here. We'll take and draw an example of a primary substrate. Let's just take a ethyl group, attach it to a leaving group, still generic for now. And the carbon that undergoes the reaction is this one. So let's actually try and draw this out a little bit differently. So this is our molecule, and this is the location where the nucleophile has to find its way. So we'll just draw a nucleophile over here. So I want you to take this ethyl substrate. I want us to kind of draw it out. My drawing isn't great like usual, but that's not the point. I want you to draw it in an expanded notation with a chiral center here. Or not a chiral center, I guess, but draw it with dashes and wedges, and then just draw a large methyl group here. So for this reaction to take place, this nucleophile has to find its way to here. It can't go through this group here. This is kind of bulky. Literally, the nucleophile is going to have to find its way here. And when it does, only then can this particular bond break. So it has to dodge this bulky substrate. The reason it does is because this is made with electrons, and this is a pair of electrons, and electrons repel one another. So to actually find its way here, it has to kind of work its way around. And this is called bulk or steric bulk. So let's take this particular substrate. It's a primary substrate. And you could imagine right away if we put at this location here, what if we replaced this location with a methyl group? Hydrogen is very small, but what if we put a methyl group here? This substrate would then become a secondary substrate. And it would be even harder for this nucleophile to find its way to the small location on the backside of carbon. The reaction would get slower. On the other hand, if we actually made this a methyl substrate, right now it's primary, this carbon's attached to one carbon, but if we want to make a methyl substrate, we could subtract this group and put a hydrogen here, and then a nucleophile would much more easily find this. So again, this is something you could build with your model kit, see the effects of steric bulk and solidify this concept in your mind. If we were going the opposite direction, or we went to methyl, we went to secondary, but let's put in a methyl group here, here, and here, and make this a tertiary substrate. There's a big methyl group here, there's actually no way for the nucleophile to find this location anymore. So as this gets bigger and more bulky, reaction gets slower, or sometimes impossible. This is an ethyl substrate. Let's actually compare it to another primary substrate. Let's change the substrate just a little bit. I'm going to put a few extra accoutrements onto our substrate. This is still primary, just like the ethyl substrate was. So drawn kind of like it's an ethyl group, but then I replaced all the hydrogens at this position with methyl groups. So I kind of put these groups on here. This has a particular name. It's neopentyl. Name isn't important for us. But please note that these are both primary substrates. Where there's a leaving group, we look right there. That's where we identify what type of substrate it is. Methyl, primary, secondary, tertiary. These are both primary. But one thing we should note right away is that this should be much bulkier than this one. So what we're going to do is we're going to just draw this out in a semi-three-dimensional way. And we're just going to see very briefly that not all primary substrates are even equal. So we're going to compare ethyl to neopentyl. And let's draw this out again. We'll draw our methylene fragment. And then in the back, we'll draw our carbon. And then to that, there's 3 methyl groups attached. Okay. So again, your goal is just to draw this out in a bigger fashion. And kind of mimicking this a little bit. Some of the features are the same. Carbon's attached to 2 hydrogens and an X group. But then I just want you to replace the methyl group we drew here with a T-butyl group. And this is much, much, much bigger. We have a big group here, big group here, big group here. And this nucleophile was trying to find this location. You should have the sense right now that even though these are both primary, they're not equal. And this one would be slower than ethyl. For the same reasons that ethyl is better than a secondary one, or methyl. It sits right here between methyl and secondary because of some steric bulk. But even amongst primary substrates, there is variation. And again, if we put more bulk in, we would predict that this one would be faster than this one, even though they're both primary. Point is, this trend is based on steric bulk at the carbon attached to the leaving group. Smaller substituents, less substituents, more hydrogens is better because nucleophile can find it. Nucleophiles are going to have a tougher time getting here past this sea of methyl groups. Okay, so the nature of the substrate is in fact a steric trend or a bulk trend. This should be very easily for us to understand in these particular problems. Steric bulk and size are something you all easily understand what's big or small. If you don't, build these two things, and then just take like a little orange or green or yellow ball, and just try and imagine with your hands it finding this little location. Just imagine that which one of these would be easier. So the question here, there's a question to me about, could we say tertiary substrate does not undergo SN2 reaction? So these groups here don't play a role in adding positive charge here at all. That's not the reason why. So the question was, as we put more of these carbon-containing groups here, we've learned that carbon can donate electrons to locations where there's partial positive charge. That's a very important trend, but that's the most important. It's not important for this particular reaction. This reaction doesn't work because of steric bulk. The bigger these groups are, these are clouds of electrons, and this thing can actually never find this particular carbon is the point. So as these groups get so cloudy and bulky and big and full of electrons, the nucleophile can never actually get close enough to make it here. So it's a great question you asked. I was asked privately, and it's just about the positive charge that's building up here. But this particular trend about tertiary being unreactive, it's dominated by the fact that as this gets so big, you never can make it here with your nucleophile. So that's a great question. And if we have more bulky groups like a secondary or a primary or these big groups, reactivity just gets slow. So keep this trend just a size trend. That'll be very, very easier for you to digest when looking at problems and evaluating, oh, this should be faster than this. If we had a methyl one, that'd be very fast. If we had a tertiary one, we would expect it wouldn't react at all. Okay, so I do appreciate that question. It's good thinking about relating charge to it. We'll use that idea later, and everyone will see what this question is about. But for this substrate, it's all about size for the SN2.